what are these? V is cutting velocity. Yeah, area is a area of undeformed chip. So this is area, not the amount of heat that is going. That is the same A we have used the previous derivation. A was different. Okay, amount of temperature that is going into it. Mu is specific cutting energy. So that is energy by MRR. You can write it as okay, F into D by MRR. Now K is thermal conductivity of the material. Rho C is volumetric specific heat of the material. Okay. So now you write the theta T. What is its dimension? It is a temperature. So temperature is represented with theta. Okay, in dimensional analysis. You all know this. Velocity V equal to meter per time or the length by time. So length means L, time. Okay, 1 by time is so capital T to the power minus 1. Area. So that is length into length or okay, length into width. So it will be meter square. So L square. Mu is force into D, then divided by volume. D is depth of cut only. So force is MLT power minus 2, L for D. Volume means LQ. So finally it will be ML inverse T power minus 2. K is nothing but energy divided by time into temperature into length. Okay. So you can write energy as ml square T power minus 2. Time is T, temperature theta, length L. So this is the dimensional analysis related equation for K. Rho C is energy divided by volume into temperature. So if you convert this, energy is anyhow ml square T power minus 2, volume is L cube, temperature theta. So this is the equation. Now what will we do after this? We'll assume okay some A, B, C, D, E like that, some powers. So theta T is proportional to this V to the power A, capital A to the power B, mu to the power C, K to the power D, rho C to the power E. Now you will write those dimensional analysis equations for all these parameters like V, A, mu, K, rho C. Theta T for that theta. For V, this is LT power minus 1 to the power A. Similarly, for A, you have written L square. For mu, ML power minus 1 T power minus 2. K, MLT power minus 3 theta power minus 1. And for rho, this is the thing. Now you equate the powers on either side. So you consider powers of L, powers of T, powers of theta, powers of M, etc. on either side and equate them. Okay. So if you consider the powers of M, so there is no M on left hand side, that will be 0. M power 0 otherwise. So that is for M it is 0 on left hand side. So for right hand side, if you consider, it is C, okay, C plus D plus E, that is equal to 0. Similarly, for L, you can write it like this: A plus 2B minus C plus D minus C. Okay, L is everywhere. L here, here. Then T. If you equate the powers of T, this is the equation. Now, if you equate the powers of theta, so only theta is there on the left hand side. So theta power 1. So minus T minus E is equal to 1. Okay. Now here we have 5 unknowns and 4 equations only. Okay, A, B, C, D, E are the unknowns, and we have 4 equations. So we cannot solve these equations directly unless we know at least one of the values A, B, C, D, E. So for that purpose, one value is assumed. Okay, so that is here. Small d is assumed as -2. Okay, why it is -2 only? So you can do some calculations and find out. Okay, if I assume -2 for d, okay, so then what will be e value? E value. So this will be 1. Okay, so that's why. Otherwise, you can assume e as 1 and d will get. We are considering this equation. Okay, and we are making those. Okay, instead of fractions, we are trying to get the whole values. So that's why d is assumed as -2. And so that is, meaning is, if you are assuming d as -2, we are assuming that theta t is proportional to 1 by k square. Okay, for k, okay, we have d. So that's why. So from that you can get the remaining values. E will become 1. C will also become 1 from the other equation once you know D and E. So then you can get A as 2 from equation 3. B is equal to 1 from equation 2. Okay. Now you substitute all these. So it will be like this. Theta t is proportional to V square A mu k power -2 rho C. Now this alone is not sufficient actually. This is giving the information related to proportionality, but there is some constant also. Okay, if you want to equate it, we need some constant times of this V square A mu k power -2 rho C, etc. So that constant can be obtained from experimental data only. So analytical method derived by Nathan Cook from dimensional analysis using experimental data for various workpiece materials. So based on the experimental data, okay, so this kind of equation was derived by Nathan Cook. This is another equation, okay? Not the previous equation. So for the previous equation that was over. So if you have some experimental data, then you can use that method and okay, find out the temperature. Based on the experimental data, so Nathan Cook has derived this empirical equation. This is different. T is temperature rise at a tool chip interface. Okay, that is in Fahrenheit. Okay, because you are taking 0.4, 0.33, etc. So in that case, it will be in Fahrenheit as per the equation derived by Nathan Cook. U is a specific energy. So that is energy by volume. V is the cutting speed, mm per second. TO is a chip thickness before cut. You all know that in mm. So those units are also important. Okay. Rho C, volumetric specific heat of workpiece material. K is thermal diffusivity. Square for second. Now, you consider the simple turning process. So we are simplifying the equations. We can write temperature is proportional to V and F. So velocity and feed only in turning process. Okay. So this is assumption only. Okay. Temperature is proportional to V and F. Temperature is definitely dependent on V and F. But we are not considering the other factors, okay, which are also influencing this temperature. Maybe depth of cut will also influence. Okay, and the environment, other things are also there. But majorly speed and feed. So because these are the different equations given by different scientists or researchers, okay, based on the experimental data. So V is equal to velocity, F is the feed rate. So for carbide tool, A is equal to 0.2, B is equal to 0.125. Now from where we have got this AB, based on experimental data only, number of experiments are conducted. Okay, so temperature is some constant into P power A, F power B. That was assumed. So then A and B are determined. Similarly, for HSS material, A equal to 0.5, B equal to 0.375. Now, once you estimation is one thing. Now, important thing is you have to control the temperature, or you have to minimize the temperature during cutting process. Otherwise, we have some adverse effects that we have discussed earlier. Now, how do we control this? So, first thing is proper selection of material and geometry of the cutting tool. This is very, very important. So, while selecting the cutting tool material, okay, you have to select the cutting tool material which can withstand high temperatures, okay, and which will have less friction with the workpiece material. Okay, so there should be less friction between the workpiece material and the tool material. Then the material workpiece chip will easily slide over. The tool temperature generation will be less. Okay. So and geometry is also important. Okay, you take very less, not very less, high rake angle, so that the chip will easily slide. If the rake angle is increasing, okay, up to some extent, the chip will be in contact. Okay, interaction will be more between the chip and the rake face, etc. So carefully select the tool material and its geometry. That is one thing. And you have to select this cutting speed and feed combination, because in turning we have understood that it is proportional to V and F. Feed and speed combination has to be selected carefully, and of course when we are reducing the feed speed, obviously you are compromising on material removal rate. So there should be one compromise between material removal rate and the temperature that is generated. Okay, if you want to reduce the temperature, your MRR will be less. Okay, if you want to increase the MRR, temperature will be more. So there should be some optimization. Okay. Now, proper selection and application of cutting fluid. This is also very important. So one thing is using cutting fluid. If you are using cutting fluid, so that fluid will take away majority of the heat, or at least major amount of the heat will be taken away by the cutting fluid. and you have to use the proper cutting fluid also. There are different types of cutting fluids for the given application. So you have to select the proper cutting fluid. So how to select the cutting fluids, etc. There is a separate topic. We'll see that later. Now, if possible, apply some special technique to reduce the cutting tool temperature. Now, what can be this special technique? You can use some special environment, okay, like cryogenic environment, etc. Okay, or by providing some special arrangement for the cutting fluid or the coolant supply. Understand? You can make the tool holder will be there. No? Inside the tool holder also you can make a channel, and cutting fluid can flow inside that, and it will take away the heat from the cutting zone. But you need a special tool for that, and you need one setup for supplying the cutting fluid through the cutting tool, okay, etc. You can make such kind of special arrangements and reduce the temperature that is generated. Now, all of you make a note of this problem, and we'll try to solve this. So you can just go through it and note down what is given. Okay, note down the data in the known notations. So analytically estimate the average shear zone temperature, that is theta S. So analytically, we have seen one derivation earlier. So based on that, you can do this. So estimate theta S for plain turning of a mild steel rod of diameter 100 mm by a carbide tool of geometry. So geometry in NRS system is given. Okay. Speed is given, feed is given, depth of cut is also given. Dry condition. So some more details like main cutting force component, that is FC, for 100 Newton. Frictional force, that is capital F, is 500 Newton. Chip thickness is given 0.6 mm. Chip thickness means the cut chip thickness, or TC. Now few more information is also given. 80% of mechanical energy gets converted into heat. 90% of the heat generated at the shear zone goes into the chip, A and Q. Mechanical equivalent of heat J is also given. It may not be given sometimes. You should be aware of this. Capital J is 4.2 joule per calorie. Volume specific heat of mild steel is also given, rho V. Ambient temperature is also given. Now note down the given data. Then simply substitute this data in equation. You will get the required theta S. All of you just go back and of course I don't know, you may not be having this. So just a second, I'll go back and show you the equation. We'll take that equation. So this is the equation. Okay. Theta S is this. So this is the equation plus room temperature also you have to take. Now in our problem, capital A is given. How much is capital A? Just tell me the data.
Point 0.9, sir.
0.9. 80% of mechanical energy gets converted. This is zero point 0.8, isn't it? Q is 0.9. Understand? Q is 0.9.
Yes, sir, understood.
So that is A and Q are given. And you know feed is also given. What is feed? Note down the given data 0.12 mm per revolution. Here I don't have this writing pad here. So just mm per revolution. All of you note down this. I'll dictate. Then uncut chip thickness T0 is 3 mm. Okay. Then cutting force is given. Okay. FC is 1200 Newton. Capital F is also given. That is okay. And now how will you find V? Cutting velocity is not given but indirectly given. How will you find out cutting velocity? Pi dn by 1000. Okay. Pi dn by 1000. Then you will get V in meter per minute. Okay. So you find out that. Yeah, anybody? Please find out V. Pi dn by 1000. RPM is also given 400. What is V? V will be equal to 125.6. 125.6 meter per minute. So, and find out VC, okay, chip velocity. Chip velocity, if you want to find chip velocity, so directly we cannot find, okay. And we know one thing, R, okay, R is equal to, what is our cutting ratio? It is TO by TC. Now here also we know TC, we don't know TO. Now how will you find TO? What is TO?
Depth of cut.
No, that is the issue. If you have this tool geometry, you have to consider that phi angle. This angle you have to consider if you have. Otherwise, assume as depth of cut. So this inclination is there, phi. Okay. Consider that. So F into sine phi. So always remember this. Okay. Previously also I have told. F sine phi. Understood. Divided by TC. Now find that R value And based on that, now once you know R value, now you can write, okay, R is also equal to VC by V, isn't it? Chip velocity by cutting velocity. This also we have seen previously. So from that, you find out VC. Okay. So this VC value will be, okay, if you find VC, it is 24.26. 24.26 meter per minute. Now once you get this, you use the equation, okay, that shown to you, theta s is equal to, okay. Now here when you are using this capital J value, you have to be careful. If all the units are in meters, okay, like that, you will already get, okay, there is no need of using J value. Understand? If it is in calories, if you have all the data in, you are getting energy in calories, then only you have to use capital J for the conversion purpose. Understand? So here, what is given here is 3554 kilojoule per meter cube degree Celsius. It is already given in kilojoule. So no need to take any J conversion value. Okay, if it is given in okay calories only, then you take J as 4.2. Understand? Otherwise, there is no need. So in this case, no need to use 4.2 J value. So if you do the calculation, and of course you have to add the ambient temperature also, 25 degrees. So final value is 643 degrees. Theta S is 643 degrees. So I am leaving it to you. All the data is given to you. I have noted down all the data. I have told the complete procedure, and the equation is also available. But here writing is a little bit difficult for me. Okay. So this is how you can solve a problem related to theta S. Okay. Similarly, you can solve other problems related to experimental data also. Okay. If it is said that this temperature is proportional to V and F, so V power A, F power B, experimental information will be given maybe in tabular form. So based on that, you can find A and B values. Okay, like that. So that's all for these thermal aspects in metal cutting. Any doubts here in today's class? Actually, I was suffering from this cold, etc. So now I'll try to share all the information with you, like all the recorded lectures. So I'll contact CR and take those lectures. And PPTs also, I'll share them immediately till today's class. By tomorrow, okay, all the information will be shared. What else? Yeah, I'll enable this review option for your minor one also. Today only I will do that and inform. Anything to discuss regarding today's topic or any other thing in machining science?
So one doubt regarding yesterday's class.
Hmm.
Last topic we've studied yesterday was micro hardness, no, sir. Is there any difference between a normal hardness test and the micro hardness thing?
Yes. See, micro hardness test is used when you are expecting that the change is at the surface level only. Okay. And hardness test is used when you are thinking that when you want to take the bulk property of the material. So here, because the temperature, okay, during cutting process is a surface process only. It is, suppose if you go to the middle of the cutting tool or to some depth, etc. Okay, you will not have the same hardness. At the surface level, it is heated up, so its hardness will be less, and at the subsurface level, hardness will be more. So if you measure normal hardness, okay, your value may be higher. If you measure micro hardness, so then you will have less hardness. Our intention is here to focus on the temperature. Okay, so temperature is in the surface level only. Okay, if you go too deep, you will not get any variation in micro hardness. You may be getting the similar micro hardness even though surface temperature is different. Understood?
Yes, sir. Understood. Thank you, sir.
Yeah, that's all for today. Thank you. Have a good day. We'll meet again in the next class.